Welcome to this fourth video in the series on the road to quantum reality. So far, there's been an introductory video, a video on the postulates that I've adopted in this work, and a video on the way to add up waves so that any angular momentum present can be estimated. In this video, we're going to look at the first application of the theory to one dimension. It may be somewhat surprising that we're looking at one dimension because the whole concept of spin in acoustic wave fields requires at least two dimensions. The reason for one dimension is slightly historic because I only found out how to do the calculations in one dimension initially. However, the results that were obtained were very revealing of a general feature of real wave quantum mechanics, and I'd like to share with you the emotional journey that I went through in getting these initial results. You may remember that in the last video we examined ways in which we could quantify the angular momentum at each FR resulting from the contributions from every other FR in some hypothetical stable structure. We found that for positive spin, mathematically speaking, we needed to take the difference between the direction of approach of each wave and its phase on arrival. This gave a complex vector which we could sum with all the other contributions in the complex plane. The final vector, shown as the red line in this figure, gave us an estimate of the spin angular momentum at the FR in question. Now, it is one thing to know what you're looking for, but quite another to know how to find it, and for some time I was bemused and confused about how to proceed. During that time I tried some fairly crazy ideas. I was rescued from my dilemma by watching a YouTube video by Mr. P. Salver or Luke Polson. I cannot recommend this channel highly enough to anyone who is interested in computational physics. Luke not only presents the theory required, but also shows in great detail how you can implement it. In this video, he shows how the Schrodinger equation can be solved in one dimension for any potential field. The method used solves Schrodinger's equation expressed as finite differences. The equation is used to construct a matrix as illustrated here. Looking at the second row, we can read off the equation at the bottom of the slide. This is essentially the finite difference expression for psi2 in terms of the value of psi either side in a row of psi values. The central term introduces the potential value which will be found in the Hamiltonian of the Schrodinger equation. A key thing to notice is that apart from three diagonal rows, every value in the matrix is 0. In Python SciPy there are special functions for building these tridiagonal matrices and solving eigenvalue problems such as these. When this program is applied to a simple harmonic oscillator potential, such as the parabolic one illustrated here, the results obtained in this slide were found. To keep the graph reasonably simple, only the results for the first, second, third and 16th eigenvectors have been plotted. The numbers on the x-axis refer to each discretization point in the finite difference application, while the plot itself is of psi star psi. The reason why this method for solving Schrodinger's equation was so helpful is that it illustrates that a very similar matrix can be applied to real-wave quantum mechanics. The key difference is now that rather than the matrix being tridiagonal, we must have an entry at every point, since every other FR is making a contribution to the vector sum at each particular FR. The matrix is not sparse. Fortunately, there are routines in SciPy for solving eigenvalue problems with full matrices. Obviously, there is a lot more computation work involved. By the way, those of you with a more mathematical background than me might see trouble brewing in this matrix. Fortunately, I didn't see it coming, so I pressed on. And this is what I got. I can hardly explain the sense of elation which I felt when I first got these results. My initial concern was that I had rerun the Schrodinger equation program by mistake. Now, admittedly, the comparison was not this exact for my first runs. I have had to adjust some of the parameters in the real wave quantum mechanics results to make them look more comparable. However, the key fact is that such a comparison can be made at all. It seems to show that there is some deep mathematical isomorphism between Schrodinger's equation and real wave quantum mechanics. For a few days, my elation with this comparison gradually ebbed away into confusion. It is one thing to see such a comparison, but quite another to understand how it could come about. It's crazy. Something's wrong somewhere. There has to be a mistake. I got the first indication of what was happening when I took a closer look at the results. Instead of plotting psi conjugate times psi, I plotted the phase of psi. Here we are looking at the central portion of the first eigenvector in the last diagram. In this close-up figure, it becomes apparent that although the magnitude squared is an exact match for the Schrodinger results, the phase is alternating from FR to FR by pi radians. For a few days, I was quite despondent that the results did not properly match those from the Schrodinger equation. It seemed as though the theory had got so close, but still got it wrong. How could it have worked? As my thought processes progressed, I became aware of the flaw in the whole concept, which some of you might have seen coming. If you look at the equation for 1FR presented at the bottom of this slide, you will see that it actually contains a harmonic series in alpha, but the harmonic series does not converge. The implication is that there will always be positive contributions from other FRs, and in addition there will be the positive gain arising from the potential term. With only positive gains at each FR, how could stable structures possibly be formed? But the thing about mathematics is that it is much smarter than I am. Remember, my discriminators are doing phase addition in the complex plane. Two vectors with the same magnitude and opposite phase cancel each other out. If phases are alternating, this is equivalent to them having positive and negative signs in the summation. So what was a harmonic series becomes an alternating harmonic series, and these do converge. So the revelation is that I hadn't found a bug, I had found a feature. It is not apparent yet, but phase alternation is going to explain the fermionic nature of electrons and positrons. But we still don't understand why we got a match with the Schrodinger results. I think this is enough excitement for one video, so we will carry on looking at this in the next video. If you are mathematically minded, be aware that in that video I might need a bit of help. Meanwhile, I will leave you with this picture of a three-dimensional structure calculated using real wave quantum mechanics.